Welcome to our review for Exam 3. Number 1, true or false. When something is true, you have to either prove that it's true, or else you have to give a definition or a theorem showing that it's true. If something is false, all we have to do is provide a counterexample. In the first one, if a sub n is greater than 0, and the sum from n equals 1 to infinity of a sub n converges, then the sum from n equals 1 to infinity of a sub n is absolutely convergent. This is true. We know that if a sub n is greater than 0, then a sub n is equal to the absolute value of a sub n. If the sum from n equals 1 to infinity of a sub n converges, then the sum from n equals 1 to infinity of the absolute value of a sub n converges. And so the sum from n equals 1 to infinity of a sub n is absolutely convergent by definition. In the second one, if the sum from n equals 1 to infinity of a sub n converges, then the sum from n equals 1 to infinity of negative 1 to the n of a sub n must converge. This is false. To prove something is false, all we have to do is give a counterexample. Let's let a sub n equal negative 1 to the n over n. Then the sum from n equals 1 to infinity of negative 1 to the n over n converges by the alternating series test, but the sum from n equals 1 to infinity of negative 1 to the n times a sub n is equal to the sum from n equals 1 to infinity of negative 1 to the n, and in place of a sub n, we sub in negative 1 to the n over n. The negative 1's cancel out, leaving us with the sum from n equals 1 to infinity of 1 over n, which diverges because it's the harmonic series. In the next one, we have the sum from n equals 1 to infinity of the absolute value of a sub n. If this converges, then the sum from n equals 1 to infinity of a sub n must converge. This is true because it's the absolute convergence theorem. For the last one, we have if the sum from n equals 1 to infinity of a sub n diverges, then the sum from n equals 1 to infinity of the absolute value of a sub n diverges. This is also true. It's the contrapositive of the absolute convergence theorem. Contrapositive means if we swap the order of the absolute convergence theorem and we negate each statement, then what we get back must be true. Swapping the order, we would have if the series a sub n diverges, then the absolute value of the series must diverge as well. Contrapositives of theorems are always true. If you see a true-false question on the exam, this is the amount of work that you should show and the general approach that you should take. In example 2, we want to demonstrate whether the alternating series converges or diverges. As always, we'll start by naming our test, the alternating series test. Before we can use the alternating series test, we have to prove the hypotheses are true. 1, we need the limit as n approaches infinity of b sub n, which in our case is n over 2n squared plus 1 to equal 0. Right now, it's in an indeterminate infinity over infinity form. And anytime you're evaluating a limit in this form, where you have a polynomial in the numerator and the denominator, you want to multiply both the numerator and the denominator by 1 over the highest powered term in the denominator. In this case, the highest powered term is n squared, so let's multiply both the numerator and the denominator by 1 over n squared. This is equal to the limit as n approaches infinity. In the numerator, we have 1 over n. In the denominator, we have 2 plus 1 over n squared. As n goes to infinity, the numerator goes to 0, and the denominator goes to 2 plus 0, which simplifies to 0, as desired. We also need to show that the terms are decreasing. We want b sub n plus 1 to be less than b sub n. Subbing n plus 1 into our b sub n, we have n plus 1 over 2 times n plus 1 quantity squared plus 1 less than n over 2n squared plus 1. If we had a 1 in both of these numerators, we could say this was clearly true for all n greater than or equal to 1. But since we don't, we can cross-multiply to show that this inequality is true instead. This is true if and only if, cross-multiplying, we have n plus 1 times 2n squared plus 1 less than n times, foiling the n plus 1 quantity squared and distributing the 2 gives us 2n squared plus 4n plus 2 plus 1, which is plus 3. This is true if and only if n times 2n squared is 2n cubed plus 1 times 2n squared is 2n squared plus n times 1 plus 1 less than 2n cubed plus 4n squared plus 3n. We have a 2n cubed on both sides, so those cancel out. Subtracting 2n squared from both sides, we have on the right-hand side 4n squared minus 2n squared, which is 2n squared. Subtracting n from both sides of the equation, we have plus 2n. I'll leave the 1 on the left-hand side of the equation so that we have all positive terms on both sides of the inequality. This is true for all n greater than or equal to 1. Giving our conclusion, we have since the limit as n approaches infinity of n over 2n squared plus 1 is equal to 0, and 0 is less than n plus 1 over 2 times n plus 1 quantity squared plus 1 less than n over 2n squared plus 1 for all n greater than or equal to 1. Then the sum from n equals 1 to infinity of negative 1 to the n minus 1 times n over 2n squared plus 1 converges by the alternating series test. In part B, we want to find a bound for the absolute value of the sum from n equals 25 to infinity of negative 1 to the n minus 1 times n over 2n squared plus 1, correct to 5 decimal places. This sum from n equals 25 to infinity, that's all the terms that we're not using when we approximate the infinite sum with s sub 24. we need to use the alternating series estimation theorem, and we satisfied the hypotheses of the alternating series estimation theorem in part A above. Then we know that the size of the error is going to be less than the size of the next term. Since we're approximating the infinite sum with the partial sum up to n equals 24, the first term that we're not going to be using will be n equal to 25, giving us the inequality less than the absolute value of 25 over 2 times 25 squared plus 1. This simplifies to 25 over 1,251, and it's approximately equal to 0.01998,401, and it keeps going. We want our answer correct to 5 decimal places. So looking at the 5th decimal place, which is 8, we need to round up, giving us that the size of the error is less than 0.01999. If you're asked to find the bound for an error and you need a decimal approximation, make sure that you always round up. Example 3. We want to find the radius of convergence and later the interval of convergence for the power series from n equals 0 to infinity of -1 to the n times x to the n over 3 to the n times n plus 3. Our series has an exponential, the 3 to the n, which is our clue that we should use the ratio test. Begin, as always, by naming your test. For the ratio test, we have the limit, as n approaches infinity, of the absolute value of a sub n plus 1. So subbing in n plus 1 everywhere we see an n, we have x to the n plus 1 over 3 to the n plus 1 times n plus 1 plus 3, which is n plus 4. This is divided by a sub n, or we can think of this as times 1 over a sub n, giving us in the numerator 3 to the n times n plus 3 over x to the n. To simplify, let's group our like terms in the limit. This is equal to the limit as n approaches infinity of the absolute value of x to the n plus 1 over x to the n times 3 to the n over 3 to the n plus 1 times n plus 3 over n plus 4. As n is approaching infinity, n plus 3 over n plus 4 is indeterminate of the infinity over infinity type. To simplify this, we need to multiply both the numerator and the denominator by 1 over n. This is equal to the limit as n approaches infinity, x to the n plus 1 divided by x to the n simplifies to x. And since x is the only thing in this limit that could possibly be negative, we only need to keep the absolute value signs around x. 3 to the n over 3 to the n plus 1 simplifies to 1/3. Distributing the 1 over n, in the numerator, we have 1 plus 3 over n, and in the denominator, we have 1 plus 4 over n. As n goes to infinity, 3 over n and 4 over n both go to 0, leaving us with 1/3 times the absolute value of x. The ratio test tells us that this series is going to converge if the limit is less than 1. 1/3 times the absolute value of x will be less than 1 when the absolute value of x is less than 3, telling us that our radius of convergence is 3. Looking at our series, we know that it's centered at x equal to 0, and with a radius of 3, our endpoints are x equal to -3 and x equal to +3. To find our interval of convergence, let's start at x equal to -3. Subbing that into our series, we have the sum from n equals 0 to infinity of 1 over n plus 3. This is very similar to the harmonic series, telling us that we want to try to prove that this series diverges using the comparison test. We need to prove that 1 over n plus 3 is bigger than something that diverges. Starting with our inequality, we have 1 over n plus 3 greater than or equal to. We'd really like it if we could just say that this is greater than or equal to 1 over n, but the inequality isn't true. If we had 1 over n minus 3, then the pluses and negatives would be working in our favor. We'd be able to say 1 over n minus 3 is greater than or equal to 1 over n. But here, the pluses and minuses, they're not working in our favor. So that's when we want to use the finesse method. 1 over n plus 3 is greater than or equal to 1 over n plus 3n, which is greater than or equal to 1 over 4n, which is greater than or equal to 0 for all n, greater than or equal to 1. Notice that the inequality is not true when n is equal to 0. Our compare to series, the sum from n equals 1 to infinity of 1/4 times 1 over n diverges because it's the harmonic series. And so the sum from n equals 0 to infinity of 1 over n plus 3, which is equal to, when n is 0, we have 1/3 plus the sum from n equals 1 to infinity of 1 over n plus 3 diverges by the comparison test. Looking at our other endpoint, when x is equal to 3, we have the sum from n equals 0 to infinity of -1 to the n over n plus 3, which is an alternating series, so we want to use our alternating series test. The limit, as n approaches infinity, of 1 over n plus 3 is equal to 0. This is clearly true, since we have a 1 in the numerator, and 1 over n plus 1 plus 3 is less than or equal to 1 over n plus 3. We need that lower bound of 0 on our left-hand side of the equation. Again, this is clearly true because we have 1s in our numerators, telling us that the sum from n equals 0 to infinity of -1 to the n over n plus 3 converges by the alternating series test. We have that our interval of convergence is equal to -3 exclusive to +3 inclusive. One last side note. Notice that the sum from n equal to 0 to infinity of -1 to the n over n plus 3 is conditionally convergent since the alternating series from n equals 0 to infinity of -1 to the n over n plus 3 converges, but the sum from n equals 0 to infinity of the absolute value of the terms, -1 to the n over n plus 3, diverges. Example 4, A and B, is all about our error bounds when we're approximating the infinite series with a Taylor polynomial. In part A, we're given that the series satisfies the hypotheses of the alternating series estimation theorem, and we're looking for a bound on the error when we're approximating sine x with the 7th degree Taylor polynomial on the interval absolute value of x less than 0.6. I always start these problems in the exact same way by writing the size of the error is less than the size of the next term. We're using the finite sum from n equals 0 to 3, and so the first term that we're not using is when n is equal to 4, telling us that the size of our error will be less than the absolute value of x raised to the 2 times 4 plus 1 over 2 times 4 plus 1 factorial. This simplifies to less than the absolute value of x to the 9th power over 9 factorial. We're given that the absolute value of x has to be less than 0.6. Subbing that into our inequality, we have the absolute value of x to the 9th over 9 factorial is less than 0.6 to the 9th power over 9 factorial. This is approximately equal to 2.77714 times 10 to the negative 8. We want our answer to be correct to 4 decimal places. So looking at our 4th decimal place, 2.7771, we have that the size of the error is less than 2.7772 times 10 to the negative 8th, correct to 4 decimal places. When you're looking for a bound on the error, make sure that you always round up. In part B, we want to know for what values of x, correct to 5 decimal places, is it true that the infinite sum minus the finite sum from n equals 0 to 3 is less than 10 to the negative 10th. The size of our error is less than the size of the next term, which we want to be less than 10 to the negative 10th. The first term that we're not using will be x to the 9th over 9 factorial. We don't care if this is an overestimate or an underestimate, so we use our absolute value signs, the size of our error, less than 10 to the negative 10th. Solving for the absolute value of x, we have the absolute value of x to the 9th power is less than 9 factorial times 10 to the negative 10th. Let's take the 9th root of both sides so that we can solve for the absolute value of x less than 9 factorial times 10 to the negative 10th to the 1/9, which is approximately equal to 0.3211000 ... We want our answer correct to 5 decimal places. So looking at our 5th decimal place, we have 0.32110, giving us our final answer, the absolute value of x less than 0.32110. When you're looking for the domain of x, you should always truncate your answer. Example 5. We want to find the Taylor polynomial of degree 4 for f of x equal to e to the negative 2x plus sine of 3x centered at x equal to 0 using the definition. Anytime you are asked to find a Taylor polynomial that's either centered anywhere other than x equal to 0 or by using the definition, you have to use the table method. Let's start by finding our derivatives, filling in the first column. When n is equal to 0, we have the function itself, e to the negative 2x plus sine of 3x. At n equal to 1, we want our first derivative, negative 2 e to the negative 2x plus 3 cosine 3x. Our second derivative is 4e to the negative 2x minus 9 sine of 3x. Our third derivative is negative 8e to the negative 2x minus 27 cosine of 3x. Our fourth derivative is 16e to the negative 2x plus 81 sine of 3x. Let's evaluate our derivatives at n equal to 0 to fill in the second column. E to the 0 is 1 plus sine of 0 is 0, giving us 1. When n equals 1, we have negative 2 plus 3 equal to 1. When n is 2, 4 times e to the 0 is 4 minus 0, giving us 4. At n equal to 3, we have negative 8 minus 27, which is equal to negative 35. When n is equal to 4, 16 times e to the 0 is 16, plus 81 times sine of 0, which is 0, simplifying to plus 0, giving us 16. Filling in our last column, when n is equal to 0, we have 1 over 0 factorial times x minus 0 raised to the 0th, which simplifies to 1. When n is equal to 1, we have 1 over 1 factorial times x minus 0 to the first power, which is equal to x. When n is equal to 2, we have 4 over 2 factorial times x minus 0 squared, which is equal to 2x squared. When n is equal to 3, we have negative 35 over 3 factorial times x minus 0 cubed. That simplifies to negative 35 over 6 times x cubed. When n is equal to 4, we have 16 over 4 factorial times x minus 0 to the 4th power, which is equal to 2/3 x to the 4th. Don't forget in your final answer to sum up the last column. The 4th degree Taylor polynomial for e to the negative 2x plus sine 3x is equal to 1 plus x plus 2x squared minus 35 over 6 times x cubed plus 2/3 times x to the 4th. If you were to see a similar problem on the exam or the final, make sure that you simplify the fractions fully. In example 6, we want to find the equation of the line that contains the point 3, negative 1, 5, and is perpendicular to the plane 4x plus 2y minus 3z equal to 11. We know the equation of a line, r of t, has the form p plus dt. We're given our point to use, p equal to the vector 3, negative 1, 5. But what is our direction vector? Whenever we're dealing with problems that contain lines and planes, I think it's really helpful to draw a quick sketch. We have a plane with the normal vector equal to 4, 2, negative 3, looking at the coefficients of our x, y, and z in our equation for the plane. And we're looking for the equation of a line that is perpendicular. Notice that the direction vector of our line is parallel to the normal vector of the plane, which means that we can choose our direction vector to be equal to the normal vector. Subbing that into the equation of our line, we have that r of t is equal to the point 3, negative 1, 5, plus the direction vector 4, 2, negative 3, times t. In example 7, the following equations are of either a line, a plane, or a sphere. We want to identify each, and we'll find any appropriate characteristics, such as anchor points, direction vectors, a normal vector. If it's a sphere, we'll label the center and the radius. In part A, we have r of t is equal to the vector t, 2, 3t. This is a line, and we can write it in our standard p plus dt form by breaking it up into its components, with the point 0, 2, 0, plus the direction vector 1, 0, 3 times t. We'll label our point p and our direction vector d. In B, the x squared, y squared, and z squared should make us think sphere. To find the center of our sphere, we need to complete the square. X squared plus 2x will become a perfect square if we take half of 2, which is 1, and we square it, giving us plus 1. If we add 1 to one side of the equation, we need to add 1 to the other side of the equation to keep it balanced. Looking at our y terms, we have y squared minus 2y. To make this into a perfect square, we take half of negative 2, which is negative 1, and we square it, giving us plus 1, adding 1 to both sides. Since the z squared doesn't have any linear terms, there's no z, we can just leave this as plus z squared. Simplifying, this becomes x plus 1, quantity squared, plus y minus 1, quantity squared, plus z, and I'll put in a minus 0 as a placeholder, quantity squared, equal to 2. The equation of a sphere, though, generally has an r squared on the right-hand side of the equation so that the radius is equal to r. In order to get our right-hand side of the equation into that standard form, we need to rewrite 2 as the square root of 2, quantity squared. We have the equation of a sphere centered at negative 1, 1, 0, with a radius r equal to the square root of 2. Part C, we have capital R of t, and this is already given to us in the standard p plus dt form of a line, where our point is 2, 4, negative 1, and our direction vector is 2, negative 6, 4. In part D, we have the equation of a plane with a normal vector equal to 6, negative 1, negative 2, which are the coefficients of the x, y, and z terms. In part E, Q of t is a line, and we can break it up into its p plus dt form by writing it as the vector 4, negative 2, 3, plus negative 3, 9, negative 6, times t, where 4, negative 2, 3 is our point, and negative 3, 9, negative 6 is our direction vector for the equation of our line. We want to show that two of our lines above are parallel and the same. We know that parallel lines have parallel direction vectors. So from C and E, we have that 3 times the direction vector of r of t is equal to -2 times the direction vector of q of t. And so that tells us that capital R of t is parallel to q of t. So we've shown that the two lines are parallel, and now to show that they're the same, we need to show that they have a point in common. 0 is always a nice, easy t value to use. Subbing in 0 into q of t, we have q of 0 is equal to 4, -2, 3. And we want to look at our capital R of t and see if we can get some t value such that our x component would be 4, or we could look at our y component, setting it equal to -2, or the z component, setting that equal to 3. If we look at the x component, we have that t equal to 1 makes the x component of r of t equal to 4. Let's sub that in to r of t and see if it lines up in the y and the z component as well. R of 1 is equal to 4, -2, 3. We have parallel lines and a point in common, which means that they have every point in common. And so we've proven that R of t and Q of t are parallel and the same line. We want to show that the third line is parallel to the plane. From part A and D, let's draw a quick sketch here. We have our plane with our normal vector n and a line, R of t, that's parallel to the plane. R of t will be parallel to the plane if and only if the direction vector of r is orthogonal or perpendicular to the normal vector of the plane. And this is going to be true if and only if the dot product of the direction vector and the normal vector is equal to 0. From part A, our direction vector is 1, 0, 3. And taking the dot product of this with our normal vector from part D, 6, -1, -2, we get this is equal to 1 times 6 plus 0 times -1 plus 3 times -2, which simplifies to 6 minus 6, which is equal to 0. Since we used if and only if statements, this works to prove that the line is parallel to the plane. In example 8, we want to know if the following series are absolutely convergent, conditionally convergent, or divergent. In part A, we have a factorial, which should jump out at us as a clue that we need to use the ratio test. We have the limit as n approaches infinity of the absolute value of 1 over n plus 1 factorial times n factorial. N plus 1 factorial is n factorial times n plus 1, which means that our limit simplifies down to the limit as n approaches infinity of 1 over n plus 1, which is equal to 0. We know for the ratio test, if the limit is less than 1, then the series converges absolutely. 0 is going to be less than 1 for all n, greater than or equal to 0, telling us that our sum from n equals 0 to infinity of negative 1 to the n over n factorial converges absolutely by the ratio test. In part B, we don't have a factorial and we don't have an exponential, which means the ratio test doesn't apply. We could still take the limit, but we'd end up getting that the limit was equal to 1, and so the ratio test would be inconclusive. Instead, we should begin by seeing if the alternating series converges, and if it does, then if the absolute value of the terms, if that series converges. The sum from n equals 1 to infinity of negative 1 to the n minus 1 over n to the 3/4 converges by the alternating series test, the limit as n approaches infinity of 1 over n to the 3/4 is equal to 0, and 0 is less than 1 over n plus 1 to the 3/4, which is less than 1 over n to the 3/4 for all n greater than or equal to 1, but the sum from n equals 1 to infinity of the absolute value of our terms, negative 1 to the n minus 1 over n to the 3/4, which is equal to the sum from n equals 1 to infinity of 1 over n to the 3/4 diverges. It's a p series with p equal to 3/4, which is less than or equal to 1. And so the sum from n equals 1 to infinity of negative 1 to the n minus 1 over n to the 3/4 is conditionally convergent. In example 12, we want to find the arc length of the portion of the curve r of t equal to cosine t sine t t that lies inside the sphere x squared plus y squared plus z squared equal to 3 squared. We know the x component of r of t is cosine t, sine t is our y component, and t is our z component. Since we're looking for the portion of the curve that lies inside the sphere, we want to sub these into our equation of our sphere. Cosine of t squared plus sine of t squared plus t squared. Since we're looking for the portion of the curve inside the sphere, we don't want to let this equal to 3 squared. That would just tell us the intersection points. Instead, we want this to be less than 3 squared. We know that cosine squared t plus sine squared t is equal to 1. Subtracting 1 from both sides of our equation, we have t squared is less than 8. Taking the square root of both sides, we have the absolute value of t is less than 2 times the square root of 2. To find the arc length, we could let our bounds go from negative 2 root 2 to positive 2 root 2. But both the sphere and the curve r of t is symmetric. So instead, we can say the arc length is equal to 2 times the integral from 0 to 2 times the square root of 2 Anytime you're using symmetry, you must note it. Subbing in our arc length formula, this is the integral of the square root of the derivative of cosine t is negative sine t, quantity squared, plus the derivative of sine t is cosine t, quantity squared, plus the derivative of t is 1 dt. Once again, we have a sine squared t plus a cosine squared t, which is equal to 1. Simplifying, we have this is equal to 2 times the integral from 0 to 2 square root 2 of the square root of 1 plus 1, which is 2, dt. This is equal to 2 times the square root of 2, t, evaluated from 0 to 2 times the square root of 2. This is equal to 2 times the square root of 2 times, evaluating at our upper bound, we have 2 times the square root of 2, minus, at our lower bound, we have 0, and this simplifies to 8.